session. I hope I am audible to everyone. If so, can you please raise your hands by clicking on the raise hand button? Just give me the response so that I can know if I'm audible. Okay, great. Thanks everybody for your response. So before we begin today's session, I would like to introduce the instructor for today. So today we have here Uttam, my colleague. He is an applications engineer in COMSOL. Mr. Uttam has received his master's degree in the field of computational electromagnetics from the Indian Institute of Technology, Bombay. I would also like to let you know all that since everybody will be on mute during the session, I would request all of you to please type your questions in the questions tab. And if you feel that any of your questions are left unanswered, you can join us for the question and answer session tomorrow at 3 p.m. IST. And also, I would like to let you know that we have assignments for each of you given that will be sharing the instructions will be sharing after this session to how to submit the assignments. And please ensure to submit your assignments by tomorrow 2 p.m. IST. And also would like to let you know that this session is recorded. So, we'll be sharing the link of the recording with you after this session, and which will be available for a week after the training course. And also, I would like to mention that since if there are any glitches which comes, if there are any audio problems which comes during the sessions, we'll take around like 1 minute to get back to log in once again to the session, just to let you know if there are any problem that occurs. So with this, now I'm going to hand over the session to my colleague Uttam here. So Uttam, can you please take over?
Yes, thanks, Anushka. So welcome to the day one of Introduction to COMSOL Multiphysics. So let us start this session. If you have any questions at any time, please do not hesitate to ask us. There is a section as question tab available at your place in the pop-up box. So you can just write your questions at any time, and we will try our level best to answer all of them. And if there are still some questions which are left unanswered, you can write those questions to support@comsol.com. So let us talk about the agenda of today's session. So the first thing is we'll go through some of the recap. We have already shared you the COMSOL Learning Center videos. So we highly recommend them. Recommend that you go through those videos because that will help you to learn the basics, so that when you come over in the session for the training, you would be able to perform the analysis. And we will give some introduction to how to do multiphysics analysis. Both the examples that we will do today, fuse circuit and heat sink, are based on multiphysics analysis. So these are some of the prerequisites that we expect you guys to do. Watch these videos, CLC videos. These have been already shared with you. So I will suggest you that if you have not seen today, by tomorrow you can, or by today night, or by tomorrow early morning, you can do this, and you can ask more questions during the one-on-one session tomorrow. So these are the part of the recap that we have already shared with you guys. Okay, so let me give you the brief introduction to COMSOL Multiphysics. With COMSOL Multiphysics, you can individually perform the physics like electrical, structural, acoustics, fluid dynamics, heat transfer, or chemical. In addition to it, you can perform coupled physics. For example, you can couple electrical and structural mechanics, or you can couple electrical with heat transfer. So there is no number of limitation, the maximum number of limitation of coupling two or more physics. So you can couple n number of physics together. There are inbuilt physics interface available which performs the multiphysics coupling, but in addition to it, you can also write your own manual coupling approaches. In addition to it, you also have the equation based interfaces where you can write and solve your own equations in addition to the pre-built equations of each and every physics. You can also perform optimization, let it be shape optimization or it could be geometry optimization. You can also couple your model with any third-party tools such as MATLAB, Excel, CAD tools like SolidWorks, AutoCAD. So the model that you make is in Model Builder uh, in COMSOL. You can convert your Model Builder into an app using Application Builder. An app is a very simple user interface where you can just change the parameters and you can get very nice graphs as you can see over here. You can share this app with your colleagues who do not know COMSOL, so they can actually maneuver or change these parameters in the app and get the results. Okay, you can also export those results into a .doc format, .doc format or HTML format, and you can also email it to your supervisor or your colleagues. So let me know if you have any questions till now. Okay, so let us proceed. We are going to launch the first poll. So yeah, Anushka, can you proceed with the polls?
Sure. So we have a poll question for you all here, and we actually would like to know what is the experience with COMSOL of yours. So I'll launch this poll question right now. Yeah, I have launched the poll question, and I would request you to please click on the desired option. Let us know if you're new to COMSOL or you already have some basic experience in COMSOL or you're using COMSOL extensively. Okay, I'll give 5 seconds more. Please put in your inputs. Okay, thanks a lot, everybody. I'll just close the poll right now. Okay, so I see here that around 58% are new to COMSOL and few have like basic experience in COMSOL. So with this, I'm gonna hand over the session to Uttam so that he can proceed accordingly.
Yeah, thanks, Anushka. So yeah, so we have a very nice mix of the attendees today. So that is great to know. Okay. So I hope okay.
I wanted to know if okay, thanks.
Yeah. Yeah, so let us go. So there's a nice mix of attendees, like 50% of new and with some basic experience. So what we are going to do today is more or less on design and engineering problem. So we will see what is the engineering problem that we face while modeling a particular system or a requirement and how to overcome those engineering problems. The engineering example that we have in our hand is a aluminum fuse circuit application. So what you see over here is this is the copper domain, as you can see over here. So this is the copper domain where we give an input, and the current passes through the copper domain like this, and then it goes to the aluminum fuse wire. And this aluminum fuse wire is having a thickness of around 0.01 mm, and it passes through this aluminum fuse wire, and then it finally goes through the copper wire, and then it goes to the bottom of the PCB, that is the ground, and then it comes over here and then completes the circuit over here. So there are multiple physics. So can you guess like what are the physics that are involved in this aluminum fuse wire application? Any guesses, any intuition? Yeah. So we have quite a good response. So basically, it is of electric currents because we are giving an input as electric currents. So that is, it will result into the flow of current, and because of the flow of current, there would be losses within the fuse wire, which will result into the rise in temperature, right? And then if you want to extend this model, which we are not doing this in this today's session, you can extend the rise in temperature to the deformation of the aluminum fuse wire. And because of deformation, if the stress is being developed within the aluminum fuse wire goes more than the threshold, and which can actually amount to the breakage of the aluminum fuse wire. So what we are going to do is we are going to set up this model from scratch, and we are going to see, we're going to perform the analysis to understand the response of this aluminum fuse wire. You can see in your GoToWebinar window, there is a handout section. In that handout section, you can open the model files .pdf. Just click on that model PDF model files.pdf, and once you open it, there is a zip file, and once you download the zip file, uh, there is around 7 to 8 model files available. Okay, and once you download the zip file, it will look like this. So this is the zip file contents, right? So you need to use this fuse underscore flat underscore wire .mph bin file. So we're going to use this mph bin file. So can you just download the handout section and just unzip the files so that you have this fuse underscore flat underscore wire mph bin file with you. So I will wait a few seconds so that you guys can download the handout section file. The file looks like this. So it is this link over here. Just paste over here. I'm also sharing this with you in the chat box. Okay. So at any time, if you face some concern of unable to follow the steps that we are performing today, that would be okay, because we are also having a recorded version of this lecture. So you can go ahead and see the recording and see if any steps you have missed. Okay. So let us go to COMSOL. So I just go to, so this is the first thing that you see once you open COMSOL. Okay. So you need to go to the model wizard. Then COMSOL asks you of which the dimension of your model or your application. In our case, as you can see over here, this is a 3D geometry. Okay. So you can just go to the 3D. Okay, and then you can actually, as of now, as you already know and you have already answered, that there are three physics that we are going to solve, or just two physics to start off with, that is electric currents and the heat transfer in the fuse wire. Okay, so in that case what we will do is we will start to do this process step by step. That is, we will only run for electric currents first. We will see the currents within this system, and once we are confident of the results with the electrical circuits, we can then go ahead of coupling the losses into the heat transfer part. So let us go to AC/DC, electric fields, and add the electric current interface. Okay, just click on add. So we'll wait for a few seconds for you guys to add the geometry, that is the 3D geometry, that is the 3D, and then the electric current interface. Let me know if you face any concerns of till now. Okay, so let me know if you have already added this electric current interface. There are people who are very new to COMSOL, so for them doing the step-by-step process might not be possible. So in that case, you can just see the approach of modeling engineering problems. For the people, around 48% people who have some basic knowledge of COMSOL, they can start to do the process step by step parallelly. Okay, so what we are doing, we are trying to set up this model from scratch, right? So you need to go to once you open COMSOL, you need to go to File, New, Model Wizard, 3D. Okay, and then you go ahead and go to AC/DC, electric fields and current section, and then electric current interface. Just click on Add. Okay, so let me know if you're able to do this step till now. So this will help me to know of how many people are doing the hands-on along with me. So yeah, and it will help me to process the flow. Yeah, so yeah, you guys are able to do this. Great. Yeah, great. So now let me go to the next part. So that is a study. Okay, now if you go to the study, it asks me about which kind of study that I want to add, right? So I just go for a stationary study as of now. Different types of study will be discussed in the solver section. So I will not uh, digress to other type of studies. As of now, we'll just click on stationary and click on done. Okay, just click on stationary and click on done. Okay, so this is the first screen that you get once you open or complete the model wizard. Okay, so what you see over here, this is the model builder. Okay, and the step-by-step process to make the whole model is the following. The first thing is you make the geometry, then you add the material, then you apply the appropriate physics boundary conditions, then you mesh your geometry, then you apply a particular kind of study or analysis, and then you finally post-process your results. So your approach in the model builder is from top to bottom. Okay, so this is how your approach has to be always. Okay, another approach is to use the ribbon pane. So in the ribbon pane also you have geometry, materials, physics, mesh, study, and results. And finally, you also have the developer node, and this helps you to write your own scripts. You can also couple your own scripts with your models. Okay, and the approach that you follow in the ribbon is from left to right, as you can already see. Right. So this is the approach top to bottom in model builder and left to right in the ribbon pane that you need to follow once you try to make the model. Okay. Any questions? Please do let me know. So I have my colleagues who will assist me for the questions that you guys are asking me. So if still there are unanswered questions, we will definitely try to take those through support. Okay. Yeah. So right now, you guys have not to open any files. You just need to open COMSOL Multiphysics and follow the model wizard steps. Okay. So you just go to the file, new model wizard, 3-dimension space. I use AC/DC, electric fields and current, electric currents. Go to my study, stationary study, and that's it. So we have not added any file as of now. Okay. Once we complete the model wizard step, the first thing we need to add the geometry first. Okay, so how do you add the geometry? So if you have skipped some steps, I will suggest you to go through the recording because this session is completely getting recorded. Okay, so the first thing is to add the geometry. So what I will do, I will just right click on the geometry one and I click on import. Okay, and over here I can just click on browse and I can just send the model file. So this is the model file, fuse underscore flat underscore wire dot mps bin. So if you just double click on this, this is available in the link that we have shared with you, and just click on import. Okay, so I will wait for a few seconds for you guys to add this or import this geometry. Yeah, so there are a few questions like how is this geometry made? So this geometry is made in COMSOL only, but to save time, we are not going into the steps involved in making the geometry. Okay, so we are just trying to import the geometry and try to do engineering analysis. So the day one is to have the glimpse of COMSOL multiphysics. So we are going to have the flavor of how to do the analysis, multiphysics analysis in COMSOL. Okay. So the basic physics is very simple. You apply the current from here, it passes through the aluminum fuse wire, which undergoes losses, joule losses. And because of the joule losses, there is the rising temperature of the aluminum fuse wire. So we are trying to come up with an scope of the fuse wire, that is what is the input required to our system, so that our fuse wire doesn't melt at a particular operating current. Okay, so that is the problem statement that we have in our hand. Okay, for that we completed the model wizard, and then we added the geometry. Okay, and we imported geometry. So let me know if you're able to add this geometry. Just let me know so that I can know that you are able to add this geometry. Yeah, great. So yeah, some people are able to add the geometry. That's great to know. Okay, so now for example, you want to select some domain or boundary within this geometry, which are internal boundaries. So for that, you just need to make this as wireframe rendering. Okay, and then you point your mouse on top of it, and then just use scroller. So that I will come in some time once this comes. So usually you put your mouse on top of it like this, and then you use your scroller to move further, right? Like this, you can actually uh, choose any boundaries which are internal boundaries, okay, not external boundaries. Either you use scroller or you just point your mouse on top of the domain that you want to select, and then use your up and down keyboard buttons like this, okay, and then whichever boundary you want to select, just left click on that. Okay, this is how you need to select the internal boundaries. This is not required as of now, but there was one other question. If you right click on the geometry and move, you're able to pan your geometry, as you can see. Okay. If you left click on the geometry and move left and right, top and bottom, you're able to rotate your geometry. Okay. If you put or you press your scroller button and move forward, you're able to zoom in. And if you move back, you're able to zoom out. Okay. So these are the basic three functionalities of using the graphics user in this graphics pane of COMSOL. Okay, let me know if you're facing any issues in doing any of this. So I'll wait for a few seconds for you guys to get a hang of it. So if you just left click on the graphics pane and just move forward and backward, left and right click on the graphics pane to move to the panning, and then use the scroller to move forward and backward. Yeah. How to select individual domains? I will come to that in some time. Selecting individual domains, individual boundaries, everything, how to select them. As of now, you can just learn how to just move your geometry back and forth, move forward. Okay, so people who are stuck at the geometry, just right click on the geometry. Once you're able to complete the model wizard, just right click on the geometry and import. Okay, once you click on import, go to browse and just choose this fuse underscore flat underscore wire mph bin. Just double click on this. Okay, and then click on build all. Okay, so now the thing is, if you just zoom into this boundaries of the aluminum, it is only a boundary. Okay, this one is only a boundary. So I want to now extend this boundary using the extrude operator. Okay, so how do I do that? So just right click on the geometry. Okay, and okay, there's one more thing that I need to do. So if you just left click on the geometry one, the length unit, you can see that it's in order of meters. Okay, so you don't have a fuse wire which is in order of like 50 meters. Okay, so it's in order of meters. It's from -40, so -20 to +20, around 40 meters, 40 to 50 meters. So you need to change the length unit. So just left click on the geometry one and change the length unit from meter to mm. Okay, so I'll wait for a few seconds for you guys to do this. Change the length unit from meter to mm, and then build all. Okay, so you see that your dimensions are now in order of mm. If you have missed any of the steps, you can see the recorded videos that we have. Okay, so once you are done with the changing the length unit from meter to mm, the next is to extrude your geometry. Okay, so I hope you have changed the length unit from meter to mm. So now just right click on geometry one and click on extrude operator. Just right click on geometry one and click on extrude operator. And then you choose this boundary over here. Okay, just left click on this boundary. Okay, so if you are for this you need to enable the wireframe rendering. Okay, so if you don't enable wireframe rendering, you cannot select this domain or boundary. Okay, just enable the wireframe rendering. Okay, and then just select this boundary over here. Okay, how do I select it? I just use left click. That's it. And in the distance over here, I write like thickness. Okay, so if I write thickness over here, this is going to give me a red symbol. So I will go into the parameter and write thickness equal to so and so mm. Okay, so I'll wait for a few seconds for you guys to use this extrude operator. Okay, okay, so I think you have added this extrude operator over here. Okay, and this parameter thickness, I'm going to write in the parameter one as again the thickness as 0.1 mm. Okay, so while you define the parameter, the name remains the same. The expression is like 0.1 mm. Okay, that is 0.1 is the absolute value of the thickness, and the square bracket is the units. Okay, so always the units are written in mm, or sorry, it's written in square brackets. Okay, so now you can see that's cancel button. or the stop button or the red cross has now been gone from this extrude operator. Okay, so just write in the parameter 1 thickness as 0.1 mm. Now I go to the extrude operator and will select it. Now you can see that the aluminium, which was just the boundary, is now extruded. That is, it's now came out of the plane. So there's some thickness to that particular boundary, and that is why we use extrusion. Okay, so now it becomes a domain. So let me know if you are able to do this step. Any concern, any issues if you are facing to do this step. Wait for a few seconds for you guys to add this extrusion. Okay, so let me know if you're able to add this, able to perform this extrusion. Any issues are you facing with the extrusion? If you're able to extrude this boundary.
Uttam, sorry to interrupt. There are quite a lot of people, they are not able to do the extrude operation. Can you please repeat it?
Yeah.
Yeah.
So what I will do, I will just delete this extrusion. Okay, so now I go to the basic, that is only a boundary. Okay, so to extrude, I just right click on the geometry one and click on extrude. So once I click on extrude, I need to then select which face I want to extrude. So I just select this face. And once I select this face, the distance, how much I need to mention is thickness that I have mentioned the parameter as 0.1 mm, right? And then I click on build all. So I'll wait for a few seconds for you guys to add these steps. Yeah. So if you don't select any of these boundaries and click on this build selected, then it will ask you to provide input entities. In that case, you need to enter this face. Okay, so just make this button on, the selection on, and then just click on the face that you want to extrude. and then just click on build all. Okay, so once you've written thickness over here, you need to also write the thickness in the parameter section. Okay, parameter in this say thickness 0.1 mm. So let me know if you're able to add this extrusion. Any issues are you facing, so that we can proceed further. Yeah, looks good. So many people are able to add this. So now the next thing is to add the materials. Okay, so now you can see that the copper is made of these domains. Okay, then you have dielectric in the center domain, and then this is the aluminum domain. Okay, so the first domain that you allow you select or you add to your geometry is the domain which is having the maximum number of elements. Okay, so in this case it's the copper. So just right click on the materials, add material from library, and go to built-in, and I go to copper. Just double click on copper. So if you just double click on copper, you will see that all the domains have been assigned as copper domain. That's what we want as of now. We will see what to do next. As of now, you can just double click on copper, and you can see that all the domains have been assigned as copper. So we'll wait for a few seconds for you guys to add this. Okay, so once you've added copper, the next thing that if you go to the geometry is that you need to add the aluminum fuse wire. Okay, so just double click on aluminum, and once aluminum is added over here, just select these domains, three domains, this one. Okay, so now we should select this one, and to select the inner domain, you cannot just left click on this one. Okay, so if you do the left click, the outer domain will get selected. So you need to just move your scroller forward and then left click. Okay, so what I'm doing is this, just keep your mouse on top of it and either use your up arrow of your keyboard to move forward and backward. Okay, or use the scroller to move forward or backward. And once you select this domain, just left click on it. Okay, so we'll wait for a few seconds for you guys to add this domain. Yeah, so I will show this again. So I will just remove all the domains. So just first of all, click on the left domain, then on the right domain, and then put your mouse on top of this domain over here where you want to select, and then just use your keyboard up arrow to move forward and backward. Okay, you need to use the wireframe rendering. Please do not forget that. Okay, so up and back arrow, or top and bottom arrow of your keyboard, or the scroller. Just move your scroller up or down, or forward or backward. To roll your scroller forward or backward. And once you are selected, so the red means that it is yet to be selected. It's not selected. But if you just click on this and then you hover your mouse on top of it, and if it's showing it as green, that means that this domain is selected. Okay, these three domains are selected. Okay, so let me know if you're able to add this aluminum domain. Any issues, any concerns if you are getting, so that we can proceed forward. Yeah, so one of the question is, we have already assigned the copper domain to 689. Okay, and we are now assigning aluminum to this. Then is the copper domain being overridden? Yes, it is going to being overridden. So if you go to the copper and then you see over here, 6, 8, and 9 is being overridden. Right. One more way to select this domain is, if I just click on clear selection, is to just, if you are still facing concern of selecting the domains, you can click on paste selection. Okay, and then write the domain numbers 6, 8, 9. Okay, looks good. Yeah, so one of the question is, how do we know these domain numbers? So you need to go to the home, and in the, okay, it would be, yeah, in the help, in this Windows. So if you just click on, go on the home, on the right side there's a Windows section. Okay, in the Windows section, if you just click on selection list. Okay, in this selection list, you can either go from domain to boundaries and edges, right? So here you can see that all the domain are numbered. Okay, And you can change either do you want to have the domain, boundary, or edges. Okay, looks good. So now I have assigned copper domain, and then I have assigned the aluminum domain. Okay. The next thing is the dielectric domain. So I just right click on the air domain, add material from library. And I go to built-in, and I select the FR4 circuit board. Okay, so in the built-in, so all the materials are available in the built-in. You don't need to search anywhere else. In the built-in, go to FR4 circuit board. Just double click on this and select the domain. Okay, so I hope you're able to add this FR4, and at any time if you have misplaced the location, for example, you might have done something very terrible to your COMSOL, so it might have gone something like this. If you're new to COMSOL, there is a tendency that it might go like this. Okay, so you don't need to worry, just go to the home. Okay, and just click on reset desktop, and hopefully it should go to the original positions like this. Okay, okay, so I've defined the copper domain, aluminum domain, and FR4. Okay, the next thing is to, so I hope you guys are done with the material section. Let me know so that I can proceed further with the electrical physics. Okay, looks good. So people are able to do the steps. So the next thing is to do add the electric current interface. To do that, I just go to my PPT and see what I need to apply. So I need to apply the current over here, and I need to withdraw my current in the bottom, right? So I need to use, so can you guess which boundary condition do I need to use in electric currents if I want to apply the current in this boundary? Which boundary condition should I use? Any guesses? If you have already worked with COMSOL a little bit. Yeah, so if you use potential, then you would be only able to apply the voltage. Okay, so here you need to apply the terminal boundary condition. Exactly. So let us right click on electric currents and use terminal boundary condition. And then just select this particular boundary. Boundary number 8. Okay. So your question is how do we decide on which type of boundary condition that has to be used? So it depends on the application. For example, in my application I am applying so this fuse circuit is current driven, so I apply current boundary condition. If it is voltage driven, then you can apply the electric potential condition or terminal. In this terminal condition, you can either use current or voltage both. Okay, or if you want to have S parameters, then you use power. We have one more question as to what does boundary current source mean. So if we usually use boundary current source for tangential flow of currents. For example, there is a surface, and on that surface you want in planar currents to be present. So on through this planar. So on those kind of applications, we use boundary current source or current density on that particular surface. But in this case, we apply we want the flow of current to be normal to this surface, so we apply something like this. Okay, so I go to terminal type, use current, and over here I write it as I naught. Okay, so I parameterize my current. So this parameterization is very important when you're trying to do the design and analysis of the fuse wire. Okay, so you can think yourself as a fuse design engineer, like an engineering design problem that is in your hand, and you just try to parameterize your current, right? So you don't write the absolute value, but you write the parameter that governs that particular current. Okay, so I write I naught, and this same I naught I define in the parameter as 10 amperes. Okay, writing in square brackets. Okay, that's very important. So I'll wait for a few seconds for you guys to add this parameter. Great. So the next thing, we applied the terminal over here. The next thing is the ground. So let's just right click on the electric currents interface and click on ground boundary condition. Okay. So in the earlier case, there are two terminals. A terminal which is a cylinder which is half filled, and there's a cylinder which is fully filled. So this is a domain condition. But as of now, we are not interested in giving the domain condition. So we have used boundary conditions. After giving terminal, we use ground boundary condition. Right? Just right click on the electric currents and use ground boundary condition and apply it somewhere over here. Okay, so I'll wait for a few seconds for you guys to add this. Yeah, so there's a question on adding terminal. So I will just delete both of them and try to add both of them. So I just right click on electric current interface and I just click on terminal boundary condition. Okay, and then I select this particular boundary. Okay, in this I go to current and just write I naught. That's it. I'll wait for a few seconds for you guys to add terminal. You can manually also add this using paste selection. Okay, so you have done added this I naught in the parameter also. I naught as 10 amperes. And then I just right click on electric current and use the ground boundary condition. Okay, use the ground boundary condition and apply it to the bottom boundary. Okay, or you can just enter. So just click on broom signal over here, clear selection, and enter the boundary 8 if you are facing difficulty to select this boundary. Okay, just select this boundary. Okay, so this is how we apply the terminal boundary condition in the top, and in the bottom we use the ground boundary. Okay, one more thing is that I hope you're able to complete this step, terminal 1 and ground 1. If you see the electric currents over here, you need to remove this domain. Okay, so just keep your hover your mouse on top of it and remove this particular domain. Okay, that is domain number 7. Okay. This domain you don't want because this is the air domain. So this is specifically if you want to do some radiation analysis, and that time you need it. But as of now, you don't need it. So just remove this. So if you hover your mouse on top of it, you just go to this electric currents and hover your mouse on top of it. It should be red color. Okay. So the air domain around that fuse wire is not model, but the aluminum itself is model. Okay, so I'll wait for a few seconds for you to remove this domain number 7, or you can manually also remove. So you just go to this 7 over here, just click on a minus remove from selection. Yeah, you can also keep this 7 and add this air domain. You can also do that. Yeah, but we're not trying to model the radiation effects. We know that, or we assume that in the air the conductivity is almost 0, so we know that the current is not going to pass through the air, right? So in that case we try to remove this domain for simplicity, but at a later stage you might want to model with a very low conductivity. That also you can do. Okay, but for simplicity we try to remove the air domain as of now, because we assume that the current is going to flow through the conducting domains. So if you see the conducting domains, they have the conductivity in order of 10 power 6 Siemens per meter, and air will have a conductivity in order of 0.1, 0.01 Siemens per meter. So a difference of around 10 power 7, 10 power 8 Siemens per meter. Yeah, in the material section, it doesn't matter if you keep 7 or not. Uh, the thing that matters is which domains that you selected. So if you have removed the 7 from here, you will also see that for this, it doesn't matter which material have you assigned to the domain number 7. Okay, have you assigned it or not, it doesn't matter. Yeah, so if you just go to this electric current interface over here, and by default all domains would be there. Okay, so you just need to just hover your mouse on top of this domain and just left click on this domain. So now it would be coming in red color. That's what you want. Okay, looks good. So that's it. Meshing, just go to meshing and click on build all. As of now, we are not going to worry much about the mesh. We are going to learn more about the mesh in the meshing session day. As of now, this is okay mesh to proceed. Just go to the mesh and build all. Okay, you just visualize the mesh if you want. I will just give few seconds for you guys to visualize the mesh. And then you can just go to study one and click on compute. Yeah, so one of the question is where this ground boundary needs to be applied. So the first thing is that you need to use ground boundary condition. Okay, and once you have added this, you need to apply it to the boundary number one, that is this domain. This is below the terminal. Okay, so the people who have clicked on compute, are you guys getting the results or how is it? Okay, great. So some people are indeed getting the results. Yeah, so if you're getting an issue of undefined sigma property, then the case may be that you might not have assigned the material for all the domains. So please check the materials that you have assigned it to all the domains or not, or some domains might be missing. Okay, so always check that in first domain that you applied, you select it as all domains. Okay, in that case, at least some domain, some material would be assigned to some of the domain. Okay, and then you override it with the other domains, right? So you'll be missing some material properties. Okay, so if you are getting the issue of undefined material, okay, so just go to copper and in the selection keep all domains. Okay, and then also don't forget to remove this domain, otherwise this will be working as copper. Okay, so you will not be able to see the losses once you post process the result. Okay. So if you're still facing the issue, you can see the recording once more. We can proceed further. So the next thing is once you are done with the electrical physics, right? So you want to see or you want to couple the losses from the electrical field to the heat transfer. So it's very important to first visualize the losses in the electrical domain. Okay. So how do you do that? Just right click on the results. Okay, and just click on 3D plot group. Okay, so I've created a 3D plot group. There is one more question as to what is the significance of the meshing. So the meshing, whatever geometry that you make in COMSOL, the solver is not going to take the geometry. It's actually, the geometry is actually going to be divided into small elements. Okay, as you can see over here, so this is a volumetric elements, small domains, and then it is going to run the numerical method on this meshed geometry. Okay, so if your geometry is having a circular wire, but your mesh is so poor that making it a rectangular wire, right? So in this case, your model is going to take, or your solution would be for rectangular wire, not for circular wire. Okay, so this is a little bit poor mesh, but that's fine. As of now, I want to show the flow of modeling in COMSOL, so that's what I'm interested in. So you can just go ahead and make more finer at a later stage, but as of now, this should be fine enough. Okay, so after computing the results, that is study 1 compute, right? If this study 1 is not there, just go to the study, add study, and then add a stationary study. Okay, so after this completing the study 1, what I do is that I want to visualize the losses in the aluminum fuse wire. So what I do, I just right click on the results, add a 3D plot group. Okay, in this 3D plot group, I just right click on the 3D plot group and click on volume. Okay, in this I just write the expression as pc.qrh. This is the expression for the losses, or variable name for the losses. And if I click on plot, you will see the losses. Okay, so I will wait for a few seconds for you guys to add this volume domain and ec.qrh. There's losses in watt per meter cube. One more question on can we see the structure after meshing? Yes. So if you see the mesh, if you just go ahead and make it more refined, like finer, you will see that it will become some kind of a circular. Okay, but this is more accurate. Okay. But as of now, as people are having limited RAM or resources, I want to run the model quickly. Okay, so instead of finer, I use normal. Okay, that should be fine as of now, not a concern. Okay, so I hope you're able to visualize the volume losses, QRH. So now you want to know what exactly is QRH, right? So just click on expression, and over here you search for losses. So if you just search for losses, you will see that this is volumetric loss density electric, because there is no magnetic component as of now. So I just the electric part. So whatever variable that you want to search, you can just search over here. for terminal, one more question on which boundaries is selected. For terminal, it is boundary number 8, and for ground is boundary number 1. Yeah, now the next thing is to couple these losses in the heat transfer interface. Okay, so how do I do that? I just now need to, so over here, what I can do, I can just go to study 1. Okay, here I can write as electrical analysis, and that's what you should always be doing. You should always do the problem step by step. Okay, so for example, your first study is to perform only the electrical analysis. The second study could be to analyze the electrothermal analysis. Okay, so I just go to study 1. I change the label from study 1 to study 1. In bracket I write electrical analysis. Okay, so the next thing I need to use the heat transfer. So I just go to the study. So I need to go to the physics, add physics. Okay, and over here I can add in heat transfer in solids. Just double click on this. Again, I remove the domain number 7. I'm not interested in modeling the radiation as of now. I remove the domain number 7. So I'll wait for a few seconds for you guys to add this physics heat transfer in solids. Yeah, so if you want to see the internal equations, you can just go to this show more options and go enable the equation view. Okay, this is a little bit advanced. Just go to equation view, and over here you will be able to see in this equation view all the variables which are hardwired internally, like losses and all those things. Like QRH would also be mentioned somewhere over here. Okay, but as of now, I'm not going into much of the advanced level. Okay, so let me know if you're able to add the heat transfer in solids. Any concern, any issue to add this? Equation view, you need to just go to the show more options, the I button, and click on the equation view and click OK. So you will be able to see the equation view. Okay. So once you have added the heat transfer in solids, you just need to add some cooling condition also, because I'm looking for a steady state answer. That is at time t equal to infinity, what is the state of your system or the temperature of your system. Okay, so to do that, I just right click on heat transfer in solids, and I use heat flux boundary condition. Okay, so right click on heat transfer in solid, use heat flux boundary condition, and select the upper boundary like this. That is boundary number 7. And then I go ahead and use the convective heat flux. So I'm trying to have a cooling boundary condition, and I give a heat transfer coefficient of 5. So this boundary is getting cooled. There's some kind of flow that is happening on the top surface, which is making this boundary to be getting cooled with the heat transfer coefficient of 5 watt per meter square Kelvin. Okay, so I'll wait for a few seconds for you guys to add this. Yeah, so there's a question as to why we use convective heat flux and not the general inward heat flux. So we are trying to impose a boundary which will actually cool the system. Okay. If you are able to cool the system, then you have to use the convective heat flux. This is a cooling boundary condition. If you use general inward heat flux, that is also possible, but in that case, you need to enter a negative value. Okay. As of now, what people usually use is a convective heat flux. That means that the air is flowing around this system and it is cooling with a heat transfer coefficient of 5. Okay, so I hope this you are able to add heat transfer coefficient 5. And so now what is happening? You're heating your system and also you're cooling the system, and hence you would be able to find a steady state solution. If you don't put this heat flux, that is, you don't cool your system and only heat your system using the Joule losses, then you will not be able to find a steady state solution. That is, you will not be able to run the stationary solution. Now the system is getting heated as well as cooled down. Right. Now I can go to my study, add study, and add a stationary study. Just double click on stationary. So I'll wait a few seconds for you guys to add the stationary study. So I go to study, add study, just double click on stationary study. And over here I run both electrical and heat transfer. Okay. I go to study 2 and I write over here electrothermal analysis. Okay. Important part is that this both need to get selected. Okay. By default, both of them would be getting selected. So this is one more question on the convergence plot. So the convergence plot signifies that your system is moving towards a constant solution, or it's able to find the solution. So usually it has a relative tolerance of 10 power minus 3, and if it goes more than the tolerance, less than the tolerance value, then your system gives you the actual results. Okay. If you're using Linux system, you just need to right click on the root node. Sorry, root node, and click on Adds Study. Okay. So that's it. Just go to Study 2 and click on Compute, and see if you're able to get a converged solution or not. So in the bottom also you can see there are two system memory values. On the left side is the physical memory, that is the memory that is COMSOL that is taking of your system. On the right side is the virtual memory, that is a kind of a way to know that how much memory does COMSOL is asking from your system. So this is what is they're asking, COMSOL is asking, and this is what your computer is able to give. So if this virtual memory goes more than your current RAM limitation, then you might be seeing that your system might be getting hung. Now I go to my electric potential, that is fine. However, in the temperature, I get just constant temperature profile. So can anyone tell me what is the issue that we have? What is the issue that is present in the model right now? Why we are getting a constant temperature throughout the domain? Any guesses? Any intuition? So we are getting a lot of response, but not the correct response till now. So the heat input, have we mentioned it or not? Yeah. So yeah, So that's what I'm looking for. The concern is what we have done is that the coupling from the losses in electrical physics to the heat transfer in solid is missing, right? So the multiphysics node is missing. So if you're in your model, you're able to see a constant temperature like this, that means that the coupling is missing. You already see that there were losses, right? So you can see that the losses was there in order of 10 power 9 watt per meter cube. That's specifically very high over here. But then you're not getting any rise in temperature. That's pretty like looks like a very big concern, right? So in that case, you can troubleshoot that there is a miss of linkage between the electric currents and heat transfer. So how do I fulfill this? Just right click on the multiphysics node, right click, and click on electromagnetic heating. Okay, that's it. Just right click on multiphysics node, electromagnetic heating. So I'll wait for a few seconds for you guys to add this. Okay, so once you add this electromagnetic heating 1 and then go to study 2 and compute, you should be able to see the rise in temperature. Yeah, so now you can see that there is a rise in temperature of your system, right? Over here you can see there's a couple of questions. How do I know which option I need to select for the coupling? So over here, if you just right click, you need to couple the electric currents and heat transfer. So electromagnetic heating does that. So you can see over here. So it couples from electric circuit interface to heat transfer in solid. Okay. So for example, if you're looking for some kind of plasma application, so then you use this one. If you are looking for some kind of Peltier effect, Seebeck effect, then you use thermoelectric effect. So this option will come up when you have electric currents and heat transfer. If you have some other interfaces, then the other options will come. Okay, and the coupling as of now is one way only. Yeah, that is the losses in the electric current interface are responsible for the rise in temperature in the heat transfer. But if you want to back couple, like if there is a rise in temperature in your electric currents, does it affect the conductivity or not? In that case, you need to go to current conservation and then go to conductivity as linearized resistivity. I'm not going to go into that as of now, but this is how you can do. Okay, looks good. So now you can ask a couple of questions once you are able to gain the temperature of your fuse wire, and that is the question could be like as in what should be the maximum, what should be the minimum thickness of the aluminum fuse wire to sustain a current of 15 amperes. So in this case, what will you do? Any guesses, any intuition? Okay, so the question is what would be the minimum thickness of the fuse wire to sustain the current of 15 ampere? So as a design engineer, what do you think that you will do? Yeah, so we are already getting very interesting answers. I'll wait a few seconds for you guys to give more answers, and then I will try to say how to do this. Yeah, so that's exactly what we should be doing. That is, we need to check the, we need to perform the parametric sweep of the thickness of the aluminum fuse wire. Exactly. And we need to see if the temperature in the aluminum fuse wire is going more than the melting point of the aluminum. So how do I do that? I just go to study 2. Okay. So I just right click on study 2 and I go add a and I go to this parametric sweep. Okay. Just right click on study 2 parametric sweep. Okay. In this parametric sweep, I just click on add button and I change my range. So I just write the thickness. So it's by default it will be coming thickness only. And over here, I can put it as the form of range. The range I can put between, okay, so I can put this as of now for simplicity. I will put it as 0.05 space 0.1 and 0.15. Okay, and units as mm. Okay, this will solve my model quickly. So only 3 parameters I'm going to run for. Okay, so you just click on range. You can do it for a very long period of variation of thickness, but as of now, to quickly get the results, I'm going to use the thickness as 0.01, 0.05, 0.1 and 0.15. Okay, and that's it. Just click on compute then. Meanwhile, there's one more question as what is the difference between study 1 and study 2? So right now, there's only a difference in the parametric sweep. In the stationary study 1, you will see that if you add more physics, then it already adds the physics over here. So if you want the study 1 to do only electrical analysis, then you should go to step 1 stationary and disable the heat transfer in solids and electromagnetic heating. In this way, it will only solve for electrical analysis. Okay. In the parametric sweep, my simulation is over now. Okay, so it has run for 3 run of thickness. And for example, now I want to evaluate the temperature at this particular point as a function of this thickness. How do I do that? Just right click on the results, 1D plot group. Okay, in this I go ahead, right click on 1D plot group 9 and click on point graph. Okay, and then I choose the point that I want to evaluate, that is this point. Somewhere you can just choose in the center this point, for example 75 number point, and expression as capital T. And don't forget to change the data set from parent to electrothermal analysis straight to parametric solution. Okay, yeah, and then select this particular point and click on plot. So you can see that as the thickness is increasing, okay, you can see that the temperature is decreasing. Okay, and the same is what you can also I will wait a few seconds for you guys to do this step. Yeah, so I will repeat this step once more. That is, I just right click on the results, 1D plot group. Okay, in this 1D plot group, right click on 1D plot group and click on point graph. Okay, and then go ahead and change the dataset from parent to study to electrothermal analysis parameter solution. Okay, and in this I just select this particular point, and expression I put it as capital T and click on plot. No concerns if you are facing some issues or error. You can see this video again so that you don't miss any points over here. So the crux of what we were doing over here is the figure you can see over here. So can you tell me what has to be the, what I did do over here is the wire thickness is increased and this is the temperature. The red is the melting point of the aluminum. So can you tell me what has to be the most appropriate thickness of wire so that it doesn't melt at 15 amperes? Any guesses, any intuition from this graph? Yes, that's correct. So it's around 0.095 mm. If it is more than that, then it is good for our system to work for 15 amperes. Okay, looks good. So the next question could be like, if what is the maximum current the fuse wire with the thickness of 0.08 mm can sustain? Okay, so in this case, what will you do? Any guesses, any intuition? Yeah, so in this case, what you can do is you can do a parametric sweep of the current. Okay, so that's what we have done, and all the analysis is given to you, shared to you. So the model file that we have shared to you, it includes all this analysis. So you can go through these model files that we have shared with you today. So what we do over here, we try to do the parametric sweep of the current. Okay, and then try to see that this is the melting point, and we understand that anything less than 13 is good for the thickness of 0.08 mm. Okay, so such kind of analysis you can perform. The final question for this problem is, if we replace the aluminum material with some other material, which one will it be and why? Okay, so you can actually do some material analysis also. So you might be having materials such as aluminum, copper, stainless steel. Okay, so you can come up with figures like this. Okay, so here what you do is you try to again increase your current, perform parametric sweep of the current, and then you try to see the melting point of your structural steel, right? So now if your appliance is working for around so the maximum operating current of your appliance is around 13 ampere. Okay, so in that case, which material will you use? Any guesses, any concerns that you get? if your appliance has to work only till 13 amperes, not more than that. So in that case, which material will you use for the fuse wire? Any guesses, any intuition? Yeah, so we will use the aluminum. That is because if you choose structural steel, it will always melt. It is more than the melting point of the structural steel. So even if you work with 5 amperes, the structural steel will melt. But we want the system to work till 13 amperes at least. Okay. So in the case of copper, if you see the copper, it never melts. Even if I'm working with 15 amperes, it will not melt. So because the melting point of copper is somewhere over here. Okay, but in the case of aluminum that you can see over here, it has specifically at 13 amperes, that the crossover is at 13 amperes. Okay, so if I have my appliance around 13.5 amperes, then my aluminum will melt. So such kind of analysis you can actually perform. There's one more question on the calibration or verification of the results. So the way to verify the results would be to with the actual experimental results. So once you do the analysis, you get a trend, you try to understand and get some kind of results like intuition of about your system, and then you can create your own experimental setup and then try to validate this with the experimental results. Okay, so what are the key takeaways from the first system that we designed? That is, you performed a fully coupled system. Okay, so we performed a fully coupled system, that is electrical currents and heat transfer coupled. We tried to understand the scope of the working of the system. Okay, and we understand why it will not work in that particular scope of the concern. Right. You can also verify a system using some analytical expression or experimental results that we discussed. Okay. The last part of today's session is to discuss on the second part. Before that, I will have one more poll questions. So, yeah, Anushka, will you launch the poll question? Yeah, the poll question is what type of physics are you interested in? So are you interested in electromagnetics, structural, fluid mechanics, chemical, or it's multi-physics application that you're interested in? Yeah, so around 50% of the attendees are interested in doing multi-physics analysis. Around 10% each are electromagnetics, structural, and chemical, and then around 15% are fluid dynamics. So we have around 50%, more than 50% actually interested in multi-physics application, and that would be good, especially for the next problem that we're going to discuss. The first example also was multi-physics. The second model is also on the multi-physics. So in this case, what we do is we have an flow, inlet flow from here, and this is the outflow of the fluid. And there is a LED bulb. You can just imagine an LED bulb somewhere over here, which is having loss of around tens of watts, right? So, and this is the heat sink on the top, and this heat sink is able to give out the heat on the surrounding, in the surrounding. Okay, so in that case, what we try to understand is how can you design your heatsink? What are the modifications that you can do in the heatsink to change the operation of your system? Okay, so there could be the design questions, as it if the LED bulb is like working for 20 watts with efficiency of 50 watts, 50%. Can you predict the hotspots? Okay, so how to predict the hotspots? It would be shown to you. So, for example, over here also, if you want to do the hotspot analysis, so if you see the temperature or the losses, okay, from this also you can get to know the hotspot. So this would be the hotspot, because the losses in the domains are like in this area are like very high, right? So you try to know where is the rise in temperature. Okay, so the first question could be like, what modifications can you do to overcome these hotspots, right? So in this case, if you do this problem, the hotspot would be somewhere over here. Okay, so can you tell me what are the steps that you can do to make this heat sink to be more effective? Any guesses, any intuition? What modifications will you do to the heat sink so that it will not melt, or specifically where the hotspots are present, it will not affect that much to those areas? Wait for a few seconds for you guys to give the response. Yeah, so we have very good responses, like increasing the surface area of the heatsink. Use fins with thicker braces. Yeah, that's a amazing response. Increase the height of the pillars, uh, specifically at the hotspot. Okay. Thermal connectivity could also be changed. That is, you can have some other materials. Okay. One of the option is also taper each fin. That is also a very good suggestions. Use thinner pillars. Okay. Okay. So cooling channel is also one of the suggestions. Multiple pillars. So the awesome suggestions. So let us see some of the suggestions that we have tried. Okay, so as we said, number of pillars is one of them. Distance between the pillar, that is the density of the pillars. So where there is a hot spot, let us try to increase the number of pillars, like make it more dense. Height of the pillars, thickness of the pillars, or airflow. So you can give airflow increase or lower to see if there is some effect. Okay, or replace some material property of some other material you can use as a heat sink. Okay, so let us see the first option, right? So that is detecting the hotspot. That is the first thing. So we already know how to detect the hotspot. In addition to it, you can also use max min temperature. For example, over here, if you use the temperature plot over here, just right click on the surface plot and sorry, just right click on the temperature plot and use more plot, and you can use max min volume. Okay, with this expression as temperature, you will see where is the maximum minimum temperature, right? So you can see over here the maximum temperature is somewhere over here. Okay, minimum is somewhere over here. You also can see the average temperature of this particular material. Okay, to do that, just right click on derived values, average, volume average, and this would be required especially in your assignment today, how to evaluate the average temperature or maximum temperature. Okay, so I can just go for volume maximum also and just choose which domain that you want to select. Okay, so I choose this domain for example and change my data set from study 1 to study 2 and write my expression as capital D. Okay, and just click on evaluate. Okay, I need to choose this domain. If you change the data set, this domain goes away. So just make sure this domain is there once you change the data set, then click on evaluate. So you can see how the max temperature for all the thickness you can see over here. Okay, looks good. Okay, so once you know where is the hotspot, the next thing is to see the type of solution that you can provide. One of them could be like extending the pillar height. Okay, so you have the pillar, so you try to extrude the surface of the pillars. That could be one of the solution, right? So if I do that, I get a figure like this: average temperature in the heatsink versus extension of the pillar size. Can you tell me what has to be the best extension of pillar height, after which like what will happen? Any guess, any intuition? Yes, definitely that 2.5 is the best one, because after that the temperature saturates. Okay, so even if you are trying to have around 3 mm extension, the average temperature remains the same, so it doesn't matter then. Okay, after 2.5 meters it doesn't matter whether you have it for 3.5. Then why do you want to waste your material, right? Even 0.5 mm of material for a very large manufacturing might be cost for you, right? So in this case, 2.5 mm is the best extension of pillar height, right? The next thing could be like increasing the number of pillars. So I know that my hotspot is somewhere over here. So how about having an extra pillar over here, or having an extra pillar over here?